Good evening, and welcome to Osmosis with me, Callum, and
Me, Jamie.
we are recording this intro post recording of the episode 0 of the podcast due to some technical difficulties.
I don't
But
think
we
it's
hope
technical
you.
difficulties. I think it's just technical short-sightedness.
Okay, so
I
for
think
some
it's a brain
technical
zone.
short-sightedness, um, this first episode is titled Pizza. We hope you enjoy.
Did you read the paper?
I have read the paper. I didn't understand, like, my physics knowledge is okay, right? It's
Very good.
it's A level physics level. Um but don't think I've read a paper in 10 years, Jamie, like a scientific paper, aside from like skimming your doctorate thesis. I really don't think I've read a paper in 10 years. So it was a lot of words. It was a lot of words.
I mean, I don't know if it helps, but it felt a lot more intense than it was in my memory. Like I read this years ago, and it's been really helpful for my pizza baking. But
Well,
it,
I had never thought about it as much as this. I'd never considered it because for me, my pizza journey is pop to Morrison's, buy one of the fresh ones because they tend to be tastier, bung it in the oven.
boom,
I had never
done.
even seen a pizza oven until I used your one.
Yeah,
And
but
I
surely
became,
you've seen a fancy shop like a restaurant, and they've
yeah, but
got.
not really. I've never like looked at one. I just like ordered them and ate them.
You never thought, oh, why does that taste better?
I mean, I suppose I had noticed they tasted better, but noticing and
Right,
wondering the
right.
why, I just never occurred to me that people had given it that much thought, you know? Like I've never
Yeah,
been to Italy, for example, and had like an
oh, that's a good
Italian
point.
pizza.
That's a good point. Yeah,
Have you?
a few times.
Okay, and
A controversial opinion. We won't go there. That's all
what
right.
do you mean we won't go there? We're doing a episode 1 of a podcast about baking good pizza, and you've been to Italy for a pizza and you won't go there?
Okay. Um, my pizza's better.
Your pizza is pretty good.
I've got a huge ego. Um, I don't know. It's
You don't
different
strike
tastes.
me as having a gigantic ego
No, surely not.
often, but it's very specific things you have an ego about. It's like cooking pizza and Monster Hunter, and
That's
that's,
about it. That I've got an ego on. Yeah.
I
No,
think
it's alright. I think
understandably.
the pizza's good, but I'm not a fan of mozzarella. That's probably more to the point.
Right. I
Um,
quite like mozzarella, but like I've never
Lots of
had an
people do.
Italian mozzarella.
I'm in the
I just
minority. I recognise that.
Yeah.
Mm,
What's your opinion on like mozzarella sticks?
it's alright.
Yeah? Well,
It's alright.
fair enough.
But
Don't mind a mozzarella stick.
I'm not in
See,
it
I
for the
think
stretchy
mozzarella
cheese.
sticks. No, I think as like as a side dish, mozzarella sticks are pretty boring. Like there are so many interesting things you could have from a side. Here's a bit of cheese and some breadcrumbs. It just
But
doesn't.
yeah, mozzarella stick.
It
Not very
just
good.
doesn't hit it for me
Not very
really.
good. I can't
All right,
remember. I'm gonna go on a tangent. Um,
tangent me up.
uh, so what is this paper? So name of the paper: The Physics of Making Good Pizza. This is Andrei Varlamov et al. Or maybe three people isn't enough to warrant an et al. But Andrei
There's a
Osmosiscast
few.
and Sergio Grasso, and these are CNR Spin. That's somewhere in Italy. There is there's a national laboratory. That's got some
Is that
weight, I
Illinois,
guess.
USA as well?
I guess so.
Yeah, Illinois
Yeah.
and Italy coming together.
And Sergio is a food anthropologist. That's all you need to do a paper. Perfect.
Define anthropologist for me.
Oh,
I feel like
I don't
I've
know.
heard the word and I could use it in a sentence, but I don't know the dictionary definition.
Human studier?
An
Anthropomorphism.
expert in or student. Oh, this is fucking useful. Anthropologist, an expert in or student of anthropology. Yeah, so anthropology, the study of human societies and cultures and their development. So yeah, makes sense.
People.
He's interested in Roman pizza.
Hmm.
Not Roman pizza, Rome and pizza. Did the Romans eat pizza? I can't remember.
It was in the paper.
900.
There's a whole
I
section on
remember.
this
It's been
historical
a
paper.
while since I've read it. I'm gonna just do a control F for Rome.
All right, TLDR. Bread. Bread and tomato was
Roman.
introduced by the Neapolitans in
Yes.
1819. Raphael Esposito added mozzarella, which that was novel at the time in the late 1800s, and that was a good old nationalist position there to make it the Italian flag.
I
And
love how you've just brought nationalism into it. That's impressive. It's an impressive segue for 5 minutes.
yeah, so it's been around for ages.
Mm.
It's got a history.
I'm just really happy that my what was his name, Sergio Grasso.
Grasso.
Um, Rome and pizza and Roman pizza, and they just both make sense. I'm quite proud of that. I'm oddly proud.
So we opened up the paper with some historical lineage of pizzas. So it's been around for an age, but actually it's
Long
probably
time
until the late 1800s where it's actually formalized as a bread tomato
as a
cheese
thing.
thing. But that's nice. And then it moved over into everywhere in the world. So Europe's got its pizza, America's got its pizza,
America, yeah.
and
I've had American pizza and I'm not a big fan.
you can't leave it like that. What American pizza? Because if you read the paper, there's what have we
A
got?
lot.
We've got New York, we got Boston, Chicago, St. Louis. Lots of different pizzas in America. Describe me your American pizza.
I think the one I've probably had is like the Chicago style deep dish pizza. Yeah, the really thick ones. I'm just not a
Mm,
fan because the ones I've had. I don't know if it's because I've just had rubbish ones, but they've always had like very crunchy crusts, and I'm not a fan. I'm just not a big fan. I don't mind like a crispy crust, but a crunchy crust is not for me.
yeah, I'm not a fan of a crunchy crust.
No, I'd like a
Thin or
crisp,
crisp?
not a crunch.
Thin or crisp or a bit doughy. That's fine.
Yes, yes, I agree. I agree. I'm with you. So I think it's the Chicago style pizza that I'm
Mm.
not a big fan of. But then like I'm also not revered for my taste buds. So if you like them, I'm happy for you. You know, I'm not about to judge.
Thanks. That's good. I like Figure Five. Figure Five's great. We've got. I can only imagine that Sergio standing there.
That looks so damn tasty, Fig 5.
It's a good
If
choice.
we edit this into a video, we put Fig 5 up now. Like I'm holding my hands like this. You can put Fig 5 here if you edit it over my head.
Well, hold your hands still, please.
But you did it as well. That's two Fig 5s.
No, I can have Sergio standing there with his pizza.
It
So
does look tasty, doesn't it?
the hypothesis of this pizza paper is they're outlining from a physical perspective, from physical principles, what makes pizza cooked in a pizza oven
Yes.
better than the cake you buy at home.
As I say, it's been a while since I've read it, but I know that he speaks about like time to cook in the
Critical.
sense of like turning tables, which I thought was a really interesting mark. I'm assuming that's probably on
Yes.
your agenda somewhere.
Yeah. I scribbled that one down. That's a really good point.
Hmm.
So at least the hypothesis is that they not so much a hypothesis, but they're looking to confirm the sort of like rule of thumb for just like a default for a typical pizzioli pizza cooker.
Pizzioli. Do you know what? I keep accidentally doing an Italian accent, and I don't want to get cancelled in
You
the
should do
first
that.
episode. So I'm trying really hard to be careful and not offend.
The hypothesis is the rule of thumb they're looking to confirm is for 330 degrees Celsius in the oven, you can cook a pizza in 2 minutes, and
Yes.
that's kind of it. But you did your note on relating it to table turnover
Yeah, it's
is
here.
interesting.
The pizzaiolo can serve 50 to 60 clients within the hour. That's where I am,
It's quite a
underneath
lot.
Fig 5.
Yeah, I see. But when it's busy, they turn up the heat. It cooks in what's that?
50
25%
seconds.
less time,
Yeah,
and they can serve 25% more customers. But you get a
exactly.
subpar pizza.
But
So
I also and I think this comes up in the paper later. There's a quote. Not many people know the difference between good pizza and great pizza, and I definitely fall into that category. Like I don't mind whack the temperature up and give it to me 25% faster. I'm sure it'll still be the best pizza I've ever had.
yeah, yeah, and that's why I guess they do it. So it makes sense. So
For sure, for
it's not
sure.
a bad pizza. It's just not the
And like,
best
here's the
pizza.
thing, right? So, how do you like your toast? Do you like a blackened toast?
No, my nan does.
Okay,
Golden
so I'm
golden brown, but it's got to have
so
you
I'm
got to have a
like
crunch.
I'm like your nan. I love a blackened toast, and when I read this, however, the quality is not the same when the temperature's been raised. The bottom and the crust are a little overdone. Quote bracket slightly black end bracket. And the tomatoes are a little undercooked. Now, I don't like cold tomatoes as a general rule.
Mm-hmm.
I don't mind them on a pizza, but they're not my favourite. And I quite like a little bit of black on my crust. So, like, I'm even wondering if it's a preference, you know?
Maybe it is. Maybe it is. I think most of it comes down to preference. We cook some weird pizzas.
You, I like your pizzas a lot. Are we gonna tell me there's a segment in here when we just talk about your pizzas?
Yeah, I've definitely got something on the cards about
Are
our
you?
new
By
pizza.
the way, I'm tangenting. We can edit this. Um, what was I gonna say? I'm tangenting. Have you intentionally not shared the agenda? Isn't it just to let chaos reign?
I did share the agenda, not formally, but it's accessible. You could have read my notes.
Oh, is it in the Synology?
Oh yeah.
Haven't looked. By the way, I just noticed your mic cut out when you were laughing, which we
Yeah.
definitely don't want. So maybe you were
That could
breaking
just
the
be a
sound
Discord
limiter.
thing.
I'll keep my fingers crossed. We'll have a look afterwards.
Good note.
Okay.
Yeah, I don't know what
If,
point this will be
if not, we'll have to do
recorded.
this all again.
Oh no. I did have some weird Discord audio issues at the weekend, but
Oh, bless you.
we digress. So, physics
Back to it.
things. So,
Yes. So this is the interface
what
of and
methods?
the analogy. Yeah.
Yeah. So, what methods of heat transfer are you familiar with? There are three.
Radiation, conduction, convection.
Yes.
That's
That's
what we
it.
teach at GCSE to the little children.
Well, I mean, if it helps, there aren't
Mm.
any like sneaky ones that aren't in there. That's it.
And I understand that they basically ignore convection in this paper.
They do, yes. Yeah, there's a footnote where they said
Mm.
convection's irrelevant, which I think is yeah,
I
that makes
imagine
sense.
my logical take on that is because inside a very hot brick oven, it's going to be such high temperature and pressure in there. There's not going to be that many air particles to circulate, and there's just so much radiation. That's my. I don't know. Am I chatting rubbish?
Sorry, yeah, no, you're mostly yeah, 90% there. You tickled me there with high pressure.
Well, it would be, would it?
No, it's
No,
atmospheric.
it's the. But is it? How? No, right. You can explain this to me because if the particles inside are hot, they're going to move out,
Yes.
and then other particles move in. But as they move out, that's not actually like those particles are of a higher temperature and pressure, so they move away. So inside the pizza oven, it becomes an area of lower pressure and sucks more air in, which then gets hot and gets pushed back out. I might be chatting rubbish.
I'm not
If
sure
I
you are
am
actually.
chatting,
That was a reasonable. That was a good scientific argument.
that makes sense in my head.
Okay, maybe it's slightly higher, but it's not like high.
It's not like high pressure,
No,
right?
no.
It's warm.
Yeah,
Because
okay.
the way I think of that is I think of the crushing the can experiment that we do
Mm.
at school, where you heat up the air inside a can with a little bit of water in there to make some water vapor when you see the steam, then you plunge it bottom side whole side down into the water and the can crushes. And then I
That's
think of
really
the
cool.
submarine.
That's really cool. No, I didn't think about that.
It's really good. It's a
Hmm.
good little experiment.
I think a an aspect of that experiment is that you have a fixed volume,
Yep, because it's
which
a can.
yeah, which isn't necessarily the case in your oven. You have a big open hole,
True. I
so
mean, I have a big open. Yeah, I don't know.
yeah,
It made logical sense. We're
that's sticking
digressing
with
again.
science. That's no, I don't think this is a digression. I think this is on the point.
Okay, fair. We take those. We take those. So basically, I'm just going to provide you with hypotheses, and then we're going to check the credibility.
Yes.
I like it. I like
No,
it.
actually, no. We're not going to check the credibility because
It's a lot of extra work.
it's not the right medium for it.
True. 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 True.
So
So yeah.
we've got three laws of thermodynamics. Three modes of heat transfer. So you have
Mhm.
conductive, which um, yeah, occurs when two surfaces are in contact.
So
Can you describe?
I'm
Yeah,
gonna jump in and I'm gonna tell you the sort of the GCSE level spiel and
yeah, go on then.
that what we do at school, right? So we talk about particles that are in physical contact, wiggling, vibrating against each other.
Right.
Uh, if I line up 10 particles and I vibrate the one on the end, that vibration will pass
Hmm.
through because they're in physical contact.
So in this analogy, what would drive the rate of heat transfer
The
from
temperature
one surface to another?
difference,
Yeah, yeah.
right? Which is what we talk about in Fig 6, right?
Oh, yes, exactly. Yeah, so Fig 6 is describing the temperature profile across a
Hmm.
thermal interface, so a hot head and a cold head
Yeah,
um, over a varying time period. Yeah,
yeah.
there's a
Which
temperature
is
gradient.
which is yeah, which is why because it uses the analogy of the mum putting her hand on the head saying, "Oh, you feel hot. How does the energy
Yeah,
go?
I meant to
How does it go?"
check my laws of thermodynamics. How hot are you on your three laws?
Um, I mean, I've got Google open, if that helps.
Uh,
Not very. Although, really good pun there. How hot are you on your thermodynamics? I don't even think you realised you did that.
so your third one, you can ignore the third one. It's something to do with entropy and that one's
The
deep.
heat death of the universe. I think
Yeah,
about
heat
the
death of
heat
the
death of the
universe.
universe all the time,
Well,
actually.
no, you're just thinking about the third law of thermodynamics, basically. So,
Yeah,
good, good
fair.
stuff.
We take those.
Uh,
You know that meme that went around of like, how often do you think of the Roman Empire? Because I never think of the
I
Roman
never think of
Empire,
the Roman Empire.
right? But I think about the heat death of the universe all the time. Way too much. I'm just glad I'm only going to live for a measly 60 to 80 years and I don't have to worry about it.
Yeah, we're so dead. First law:
Oh dear.
two bodies, they're in contact. After an infinite time, they will reach equilibrium. That's it. So you got a hot thing, you got a
Yep,
cold thing. Infinite time, they'll be at the same temperature. First law.
right. Yep,
Second
makes
law.
sense. If I put a cup of tea out,
Yeah,
eventually it will become room temperature.
naturally.
So that's the first law.
Yeah,
Okay.
I'm blanking on the second one right now.
Do you want me to Google it for you?
Yeah, go on. What's the second law?
Second law thermodynamics. Second law of thermodynamics states that the state of entropy of the entire universe as an isolated system will always increase over time. So that's the heat
That's the
death of
one.
the
That's the heat death
universe.
of the universe. We don't want that one.
That's the heat death of the
Third law.
universe.
Third law, please.
Third law. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. So let me
Oh,
wrap
these are
my head around that
rubbish.
first. Is that a
Okay.
poor definition?
Nah, that's fine. But I thought there was another one. Maybe I'm thinking of the
Fourth
1.5,
law?
the 1.5 law of thermodynamics.
Hang on, I'm just trying to pass that sentence. The entropy. So entropy is disorder.
Yes.
So basically, that is saying that at absolute zero, things are as disordered as possible.
Oh no, let's read it again.
The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero,
Okay.
which would imply that at absolute zero, entropy cannot get any higher.
It says it approaches a constant value. I don't think it's a constant big value. It could be a constant small value. But my expectation would be at absolute zero. Everything is
Done.
nada, nil,
Yeah.
no motion, no entropy.
I mean,
But apparently there is entropy. It's just
is
not changing.
motion motion is energy, energy is matter, so it's just nothing.
Yeah, maybe. Ah.
Heat death of the universe. Ah, oh
Um.
god.
All right.
Let's talk
Well,
about the child's head and the mother's hand some more.
yeah. So we start off the analogy with a child's head and a mother's head, and they're reaching thermal equilibrium. We're
Child's
just
head and a
sitting,
mother. Oh yeah, sorry,
yeah,
I misread it. It is child's head and mother's head. They're touching
head to
foreheads. I thought
head.
it was hand. I thought you were
Uh,
going crazy, imagining this mum headbutting her child or
no, it's
something.
it's head to head, but um, the concept that we next approach is specific heat capacity. So if we were to replace
Oh, I hate this.
mother's head with robot mother head, then that changes everything. So now
Yes.
the due to so the equations in
I
place
can
of
give you a really good definition of specific heat
please,
capacity.
well, let's go
The
for it.
specific heat capacity is the amount of energy required to raise the temperature of a kilogram of substance by 1 Kelvin or 1 degree Celsius. That's what a perfect GCSE specification, mate.
Yeah, that's pretty good. Specific heat capacity. Uh, so the relevance of this to pizza is the
Material that it's sitting on to
exactly.
cook.
So we could be in a brick oven. We're sitting on a brick interface. So it's a dough brick interface, and then the thermal specific heat capacity of that brick will affect your thermal conduction across that interface. If
And it
we
will affect the thermal conduction because thermal conduction is dependent on the temperature difference.
Mhm. It's
Right.
dependent on the temperature difference, but also on the specific heat capacity.
Why on the specific? Because is that because of it will affect how much energy it contains?
How quickly the energy can flow. So thermal conduction is
Right.
largely governed by the heat flux across the interface. So heat
I
flux,
remember reading about heat flux is mentioned in here, isn't it?
it
I
is,
think
yeah.
that might be the bit I skipped over. Lots of maths.
So we discuss heat flux in equations like 1 through 3. So yeah, where's Q as defined? The heat flux density is the amount of delta Q that flows through a unit area per unit time in the direction of temperature change. So here the heat flux density in the equation has specific heat capacity. It has M. I'm assuming that's mass. Yeah, it's probably mass. Temperature change, and then in the denominator it's got S. S
Yeah,
is.
see, this is where the maths loses me. I'm gonna be real honest. A long old graph for cooking pizzas, a long
Yeah,
old formula.
but at least what we see here is the heat flux density is dependent on the specific
Specific
heat
heat.
capacity. So if the interface can draw more heat through it, then it will. And so in the instance of the steel, um, the metal mother, then there's more heat being drawn through that interface, or it's heating quicker.
Yeah,
It's cooking your pizza
makes
quicker,
sense.
which is why we use
Tasty.
metal things in our oven because they're efficient at what they
Yes.
do.
Yes.
So yeah, that's conductive heat transfer.
Right. Makes
And
sense. Makes sense.
the paper does some solving stuff. Oh, S is area. Oh, obviously. It's
Area
the
of the
area
pizza.
area of the interface. Yeah, exactly. Area of your pizza.
Right. Yeah.
Pi r squared.
I love that. Do you know what? My go-to starter activity on Pi Day, the 13th of or the sorry, the 14th of March, is what's more pizza? One 12-inch pizza or two 6-inch pizzas. I let them choose. Do they want to work out the area of the pizza? Well, if it's stuffed crust, do you want more crust? It's great fun. It is great fun.
Yep, that's pretty good. So convective, we don't really talk about that, and I think it makes
Where are
sense.
we? Which page are we on?
Just freewheeling here, but
Just browsing.
I'm looking at figure eight. Um, so convective heat transfer.
Yes.
The times when it would be relevant would be um, in air, which is actually an important thing because you
Yep.
take me to space or take me in a vacuum. Convection's not a thing.
Yep.
That happens quite a bit. So you need air. You need your temperature gradient across that interface, and you also need a bit more time. So convective heat transfer is not a fast thing unless it's forced. So with like a fan or something. Um,
Right.
so actually, the paper does ignore it, but I think if the paper was to be a comprehensive study on comparing brick oven to conventional ovens are often fan driven, and
When
they
we
will be
say
in there longer.
conventional oven, are we talking about what's in my kitchen,
That's
my fan
exactly what we're
oven?
talking about.
Yeah.
Yeah, yeah. So maybe convective heat transfer should be considered for comprehensive. Anyway, yeah. So we're going to ignore
Also,
convection.
we're also thinking because in my oven, like my oven, it's like a grill that the pizza sits on as well. Which so if we're talking about area, it's like a wire.
You just put it on the Y rack.
Yeah.
Hmm.
What do you put it on? A pizza tray.
I don't anymore, but yeah, you could you just put it on like a metal tray.
I just felt like that's a lot of faff.
It is, but that would
It's
affect
like
your
they.
pizza cooking time because you're just convectively heating
That's
your
that is a
pizza.
fair point, but I've just always done it like that, to be honest.
I don't think it really matters when you're cooking the type of pizza you're cooking.
What are you trying to say? It says fresh on it. I see the lady make it in Morris's. What are you saying? Just shitting on my pizza choices.
Actually, no, you did say you got the fresh one.
I
But
love. Do you know what? I
but if we were
really
fresh dough,
rate
it would
Morris's
sink through,
pizza.
right?
Yes,
Yeah, yeah, yeah,
absolutely. If
yeah.
it was fresh though, it would sink through. You're absolutely right. It would.
That's what I meant
Um,
actually.
and to be fair, I have attempted many a time in the past to make pizza, and I always make them too doughy
Mm,
or it too raw. I'm just no good. What I am is I'm okay at cooking, but I am terrible at baking. Baking is not my forte. I can't do cakes. I can't do breads. Give me some ingredients and I'll rustle you up a dinner, but I can't make bread. In it, I think the reason is because I'm way too impatient. I don't wait for it to rise enough. I never wait for it to rise enough. I can never keep the
mm,
like
mm.
it warm enough for proving. I'm just too impatient. I can't do it.
It's
But
definitely an
I'm an
art to it.
adult man that is okay with saying he can't do it these days,
It's good to
I
accept.
don't I don't dwell on it anymore.
No,
There's no
move
point
on.
in dwelling on it. I'll buy my pizza and I'll cook something else. I'll buy my cakes.
Yeah,
And anyway, I've got you. You make me pizza. That's
yeah, I
enough.
can do pizza. Third, super really important. Actually, it's really important for this aspect.
Mhm.
Radiative heat transfer. What is it?
So my understanding of radiation is that it is
Not
an
ionizing. Let's clarify here.
non-ionizing infrared electromagnetic light wave. That's my understanding.
Yeah.
What is a wave? It is a transfer of energy, I
Oh, I
suppose.
didn't want to go there, but yeah, right.
Fair enough. What is a wave? You got to remember, I come at this from GCSE. I'm actually teaching waves at the moment, and we talked about infrared today, and saying to them, so what are the dangers? What do we need to be careful of? Quite hot. What do you think? So yeah, um, that's my understanding of radiation. It is an electromagnetic wave.
Yeah. So radiative heat transfer. Do you come up? Have you come up to that much?
Nope. Enlighten
Hmm.
me.
How do you do cheese on toast?
By plopping it on the grill,
How does the
which
grill
heats it
cook?
from above.
Yeah.
Radiation would be
Yeah.
my assumption.
That's it. Yeah. So
So,
we use and we are familiar with radiative heat transfer
mhm.
in the everyday. So cheese on toast under a grill, that's radiatively heating. So it heats
So I suppose a
directionally. So there's a directionality to it. Like it doesn't cook the bottom of your toast,
Nope. Hmm.
just cooks the top. So
It's
it's
a bit like an actual toaster. That's why you've got a
yeah,
heating element on both
yeah.
sides.
Toaster's radiative heat transfer. There's no fan in there.
Mhm.
Yeah. Um. So the important aspect of radiative heat transfer is what's the temperature difference. So things have to be really, really hot to start cooking. So
So
that's why we start see
I'm
it
thinking
glow.
about like yeah, that's what I'm thinking about, like glowing,
Mm-hmm.
because you associate that, you know, if you think about the heating element in a oven or in a toaster, they do glow
Yep.
hot.
Yeah. So that sort of thing would be uh,
So for rate how would it was the word you used?
radiative heat transfer.
Radiative. For radiative heat transfer, that cares more about temperature differential than conductive.
I don't know if more than, but it's important.
As much as.
There are other
Okay.
more important things. So like actually being a hot enough temperature. So like if you and I were standing in the same room as each other, we would be radiatively heating each other
Yep.
mutually. But the
Sounds a bit
power of that,
sexual.
the power of that would be tiny wee.
Very small.
And
Yeah,
that's
we
mostly
kind
just
of
due to the the temperatures that we're looking at. So the Stefan Boltzmann law is
I
um,
recognize that.
is a description of the energy emitted, so the radiant excitance um, from a surface, and it's a very simple equation. I believe it's what was m equals sigma t to the 4. We're not going to find it. We are going to find it. Yeah. So the excitance is equal to a constant multiplied by the temperature
When you use
to
what
the
is the
power of 4.
excitance? What's that? Like the amount given
Amount
out.
exiting. Yes. Yeah.
Right,
Yeah.
right, right. I've
So
never heard that word before.
hmm. So the amount of energy given out is proportional to the fourth order of temperature. So what that means is at room temperature it's like a little bit, but if you increase it by 20 degrees, it's now like
Right, right. It's a lot
20
bigger.
to the it's a lot bigger. So
Okay, which
the
is yeah,
yeah,
okay.
so that's just super important. The times the temperatures at which it
Is
becomes more
I'm
useful.
for some reason I'm thinking of like, you know, like gravitational fields and how they are spherical.
Yes.
Is it the same sort of thing with radiative heat transfer? Is it so I have like an A level physics memory of it being like to the power of 3 because that's like the radius of a sphere or the volume of a sphere or something. I remember when we did like luminosity and we talked about brightness of stars,
Mm-hmm.
and like perceived brightness versus I mean I'm assuming it probably works the same way because the visible light from a star is the same type of wave as an infrared
Mm-hmm.
light wave.
Yep. Yeah, it's that sort of thing. So there's it's kind of related to distance, but not really. It's
Okay.
more related to the solid angle.
So I suppose what I'm asking really is how far away from the explosion do I need to be to not get burnt? You know,
Close will burn you.
for
Far away
sure.
won't do much. So
Hmm.
yeah, so it's the amount of energy it emits is t to the 4, but that is um, but that's like energy given out in all directions. So if we were to
Right.
then consider the energy that you radiate on me, it does depend on like how close I am to you. So if I'm really close, the solid angle. So if you think of a like 2-dimensional, you draw angles in your triangle. That's an angle.
Yeah.
And if you had if I have a cone, that from the pointy bit, that whole like conal part
Yeah.
is a solid angle.
Right.
So it's just like a 3D angle.
Yeah.
And so if you're really close to
Think
something,
I'm following you.
yeah. So if you're really close to something, then that solid angle is a bit bigger, and you're going to collect more of that radiation.
Yeah.
And if I'm really far
Makes
away,
sense.
like looking at a star in another galaxy, then it's still going to be really hot and emitting a lot of energy, but the
But
solid
not
angle,
much of it's getting to me.
tiny.
Yeah.
Yeah.
Yeah. Makes sense. Makes sense.
But that's yeah. That's star stuff. So like the energy it emits is a lot. And then
So
like
so to bring that back to pizza,
so the
it
temperatures where radiative heat transfer is relevant is
right,
200 degrees upwards, ishy.
okay,
So in your conventional home oven, it's not there isn't much radiative heat transfer going on.
yeah.
But when we're looking at a pizza oven where we're operating at
It's like
300,
300
400
and
degrees,
yeah, much
330
higher. Yeah,
is the rule of thumb,
much higher.
then
Much higher.
radiative heat transfer starts to become more useful.
I've got a question for you.
Please.
So let's say I've got a pizza oven, the thermostat's broken. How do I know the temperature inside? Like I can't use an infrared heat gun, surely.
Why not?
That's measuring surface temperature. How's that going to measure the
It is
temperature
measuring
of the
surface
air
temperature.
inside?
Oh,
Got him.
no, you haven't got me, but I see the size of the tangent ahead of us. um, Air temperature, surface temperature, very different things. Rightfully pointed out.
That's what I'm thinking.
Yeah. But okay, so in this case, we don't really care about air temperature in the pizza oven case. So we're ignoring air temperature because we're ignoring convection, and all we do care about is surface temperature. So I think in this case, infrared thermometer that would work
Would do the job.
because you want to know what's the temperature of the base of your oven for your conductive heat transfer. What's the temperature of the roof of your oven for your radiative heat transfer?
Right. I'm with you.
So they're both directional in that sense. So yeah,
Yes.
that thermometer would be fine.
Like a toaster, either
Like a toaster,
side.
either side.
A pizza oven's a giant toaster, case closed.
Yeah, yeah. It's a one-sided toaster. So, Stephen Boltzmann's law, T to the 4, hot things, lots of energy.
Mhm.
I don't actually have much more after this. So, I guess to wrap it up, so they built a physical model that explored two of your three heat transfer methods.
Is this table 1?
Let's have a look. I don't know what I'm looking at. I'm looking at my scribbles. So there's equations. You have fun with them. And we are looking at no, not really table one. Table one is outlining some of the physical constants that they
Right,
put into
right.
their model. So things that are so they had four materials of relevance. They had their dough, they had their steel, their brick for the oven, and their water. And the principle that they're working with is if we cooked to define cooked for this pizza, excess moisture has been evaporated.
Yeah.
And we can evaporate that through the conductive heat transfer. We can
Then they
evaporate it from
mentioned
the
that.
radiative heat
Yeah.
transfer. So these are the four materials, and then the properties that they've got are heat capacity, thermal conductivity, density, and
Yeah. So the
conductivity
reason why
again.
I remember what it says in the paper on the last page, a final trick disclosed to us is the importance of pizzas with water-rich toppings such as
Yes.
eggplant, tomato slices, or veg. In this case, the expert first bakes the pizza regularly on the oven
Mm-hmm.
surface, but when the pizza's bottom is finished, he lifts it with the spade and holds it elevated from the baking surface for another half a minute or more in order to expose the pizza to just the heat irradiation. In
Yeah.
this way, they avoid burning the dough and they cook the toppings.
Thermal conductive heat transfer stopped.
And they
Radiative heat
have them
transfer still going.
continues exactly. And I suppose any potential irradiation from the bottom, which is a hot body, if it's 390 degrees, is going
Mm-hmm.
to be insulated by the spade. Bob's your uncle.
Yeah.
Easy peasy. Cook a pizza.
Yeah.
50 seconds.
Yeah. Exactly. I quite like that. That was a good tip. Wet pizza, hold it in here.
I
Wave it
find
about.
that even with the crappy pizzas, and I don't think they're crappy, but by your metrics, even with the crappy pizzas I buy, like if I get one with veg, God, does it need a bit longer to
Mm.
cook because it just gets so runny and it does my head in.
There we go. It's just moisture. We're just
Mm,
removing moisture.
it just
So
needs more time.
perfect pizza. If we are in a brick oven, it's 330 degrees for 2 minutes. And so their thermal model, their physical model largely agreed with the Pizziolo's rule of thumb. And if you're in a conventional, like, conventional
Conventional something
convection oven,
like what we have at home.
exactly, then what do we end up with? Bottom of the pizza. So temperature of 330 degrees. It's got to be too hot. Oh no, here we go. 208 degrees. That's your perfect pizza time. Pizza temperature. I don't know how long it takes to cook. I forget the. I don't think it actually explores that. Maybe it does. I think it's a bit further down.
I can't find it, Jay.
I can't find it either. Oh, here we go. Just below equation 13. So baking time in wood, 125 seconds.
Yeah, I see
so
it.
that's 2 minutes. And then for an electric oven, it's 170 seconds. But that can't be right.
Yeah.
That can't be right.
I mean, it makes sense.
I think they get to it makes sense. It takes longer to cook because it's cooler temperature. But it's offset by the higher thermal conductivity of the steel.
Maybe we need to do it.
I think we need convective heat transfer in there. It's missing a little. That's all it's missing.
You think we need to bring convection into it afterwards?
Maybe.
After
I think
all,
so.
sorry.
I think so. For a modern oven is a convection-based oven.
I mean, I think I mean, are they thinking about the ovens we have, or are they just thinking about?
Yes, gotta be. I think so.
Is there another type of?
That's how
I don't know.
It.
That's how I interpreted it. But like, I mean, again, I'm thinking I'd never cook a pizza in 170 seconds, but then my pizzas that I cook are not fresh. Right? You can probably talk from better experience. If you were to prepare a pizza and pop it in your oven, would it cook in 170 seconds?
No.
Do you think shorter or longer?
All right. On to any other business. So this paper, definitely influential. Personally. So I read this pizza and I was using my conventional oven. I had a pizza stone. And it didn't change much. And that kind of tracks, I think. If you look at, if we follow the physics of this analysis, we're replacing the steel baking tray with a brick baking tray. So we're reducing the thermal conductivity of the interface. So it still takes, in principle, it should take longer to cook. But when you actually apply it in practice, you leave the stone to reach temperature. So you kind of ignore the additional waiting time because the stone's already at 230 degrees or 208 degrees.
Makes sense.
But it still takes 10 minutes, like normally 10 minutes to cook.
Really?
And that's because the stone's not doing much. The stone's still at the same temperature that your steel baking tray was at. It's not really doing anything different. But the key thing you're missing out there is the radiative heat transfer.
Right.
So when I could make the same dough, cook it in an oven. I could also cook it in a pizza oven that's operating at 330 degrees, and the difference between the two is noticeable.
I think we definitely need to do this one day.
Okay, yeah.
I'm down. I'm down.
Controlled experiment.
Yeah, and the best thing is we get to taste test.
Exactly. So yeah, it's radiative heat transfer, super important for pizza.
I will note that one. I will note that.
I mean, you can't do much with it in your normal oven, but
no, exactly. I suppose that's the big issue, isn't it? Because in a conventional convection oven, there isn't much short of grilling it. Can't imagine that'll work.
I think the other key takeaway from this paper is if you go to a restaurant and you order pizza, just ask them, what's the temperature of your pizza oven?
Ask the temperature. I like it. I like it. It's a very good bit of advice there.